Dear friends, today we start with a new topic, chemical bonding. It is a continuum of the session atomic structure which we have completed in the first session of this semester. What is a chemical bond? Or how it can be defined? That is the first question. It is a kind of attractive force which hold the constituent atoms or ions of a molecular species together is called a bond. Molecular species can be of neutral or ionic. Neutral molecule contain large number of atoms. The attractive force which hold these atoms together in that neutral molecule is called bonding in that molecule. In the case of charged species, there may be ions as constituent particles. Ions can be formed from a single atom or polyatoms. Anyway, there should be an attractive force to hold these ions together in a molecular species. These various kinds of attractive forces collectively called chemical bond. Actually, this chemical bond is a trick of nature to reduce the energy of the system and to make it stable. By nature, atoms can have higher energy in individual form. When they combine together, the energy of each atom get reduced and come to a stable condition. The basic theory explaining bonding is octet theory. According to this theory, introduced by Lewis and Cousel, an atom is stable if it contains 8 electrons in the valence shell or it has 8 valence electrons. If the number of valence electrons is equal to 8, that atom is considered to be stable and they are chemically inert. Example, noble gases. If the number of valence electrons is less than 8, they are seems to be unstable and they exhibit a tendency to gain 8 electrons in the valence shell by making some rearrangements. For that rearrangement, they have to part in bonding. During the chemical bonding, each of them can acquire 8 electrons in the valence shell so that they can be stabilized. To get 8 electrons in the valence shell, atoms can have two probabilities or possibilities. Either they can transfer electrons or they can share electrons. If atoms transfer electrons from one atom to another, the bond formed is ionic in nature. If they are ready to share the electrons, we have two chances of covalent bond and coordinate bond. Next session is types of bonds. Generally, chemical bonds are ionic, covalent or coordinate. We have to see it one by one. Ionic bond. It is the bond formed through the complete transfer of one or more electrons from one atom to another. number of electrons transferred can be 1 or more than 1. There is no restriction. For example, sodium configuration is 281. So valence electron is 1 in number. That electron is shown in green color. Chlorine configuration is 287. 7 electrons in the valence shell. As far as concerned with sodium, it can make the valence electrons 8 either by removing this electron or gaining 7 more electrons. In the same way, chlorine can also have two possibilities: to gain 1 more electron or remove 7 electrons. By removing this 7, this 8 will be the valence electrons. But the simplest way for both sodium and chlorine is the donation of this 1 electron by sodium to chlorine, such that 7 plus that 1 electron make it 8. In figure you can see that this green electron, the valence electron of sodium, and 7 valence electron of chlorine shown in rose color. In product side, that green electron is completely transferred to chlorine. It is now that green dot is with chlorine, and chlorine is now a species of extra electron, so Cl minus. Sodium lost its electron and acquired Na plus charge. So NaCl is established by the transfer of 1 electron from sodium to chlorine. See another example, magnesium chloride. It has the formula MgCl2, magnesium combined with 2 chlorine atoms. Magnesium belongs to second group and has 2 valence electrons shown in green color. Chlorine, as said earlier, contain 7 valence electron, which is in need of 1 more electrons. So chlorine need only 1, but magnesium need to remove 2. So 2 chlorine atoms are required to accept 2 electrons from magnesium. So 1 electron is transferred here and 1 electron is transferred here. It can be clearly shown in the product side. Green, here also green electron from magnesium. After the removal of 2 electrons, magnesium become Mg2 plus, and by gaining this electron, Cl becomes Cl minus. And see, calcium and oxygen when combined, calcium contains 2 valence electrons shown in green color, and oxygen contains 6 valence electrons shown in pink color. This 2 electron is transferred to oxygen. Then calcium 2 plus and O2 minus, calcium oxide is established. Here 1 electron is transferred. Here 2 electron is transferred to 2 different atoms. Here 2 electron is transferred to same atom. All these kinds of possibilities we have for making ionic bond. Anyway, this is the transfer of electron. That word is very important. Next, what are the factors favoring the formation of ionic bond? First factor is number of valence electrons. For the formation of an ionic bond, one element should remove its electron, lose its electron. That element is called metal. And the second element should have the capacity to accept the electron, and such elements are called non-metals. So An ionic bond is established by the interaction between a metal and non-metal. Metal is electron donor and non-metal is electron acceptor. Metal should have valence electron 1, 2 or 3, and non-metal 5, 6 or 7 valence electrons. In the case of sodium chloride, metal valence electron is 1 and non-metal valence electron is 7. In the case of calcium oxide, it is 2 and 6. All other combinations are also possible. Examples: aluminum phosphide or nitride. Aluminum donate 3 electrons and nitrogen can accept it. Then 5-3 combination is also possible. Next one is END, electronegativity difference. You have to read it, electronegativity difference. It should be greater than 1.7. In sodium chloride, electronegativity of sodium is 0.9 and chlorine is 3. Difference is 2.1. Therefore, it is greater than 1.7 and found to be ionic compound. At the same time, if we consider HCl as example, Cl is 3 and hydrogen is 2.1. Difference is just 0.9, which is far less than this cutoff value. So it is covalent, polar covalent. Third factor, which is useful for predicting the ionic bond formation, is the energy changes. The energy parameters associated with ionic bond formation are ionization energy, electron affinity and lattice energy. Ionization energy of the metal should be low so that it can easily donate its electron. If the metal possesses high ionization energy, removal of electron will become in trouble. So we prefer the metals having low ionization energy for forming ionic bond. Second one, electron affinity of non-metal should be high. A metal with low ionization energy loses its electron easily. If the non-metal is not having sufficient electron affinity, it will not have a tendency to accept that electron. Under such condition, formation of ionic bond is difficult. So to have an ionic bond easily, metal should have low ionization energy and non-metal should have high electron affinity or electron gain enthalpy. Now, lattice energy. What is lattice energy? It is the amount of energy released when 1 mole of an ionic compound is formed from its constituent ions. When 1 mole of an ionic compound is formed from its constituent ions, 1 mole NaCl can be formed from 1 mole Na plus and 1 mole Cl minus. 1 mole Na plus 1 mole Cl minus gives 1 mole NaCl. So the amount of energy released during the combination of 1 mole Na plus and 1 mole Cl minus is called lattice energy of NaCl. But for calcium chloride, 1 mole calcium plus 2 moles of Cl minus is required to form CaCl2. From the formula itself, it is very clear that 1 mole calcium and 2 moles of Cl minus are required to form 1 mole calcium chloride. The amount of energy released during the combination of 1 mole calcium with 2 moles of Cl minus is called lattice energy of calcium chloride. This lattice energy is directly proportional to charge of the ion and inversely proportional to distance between them. That is also related to size. When the size of the ion increases, distance between the ions also increases, then lattice energy decreases. When charge increases, lattice energy increases. Lattice energy can also be defined in another way. It is the amount of energy released during the formation of 1 mole NaCl, that is okay. In other term, it is the amount of energy required to disturb 1 mole of an ionic compound to its constituent ions. It is the amount of energy required to separate an ionic compound, 1 mole of ionic compound, into its constituent ions. That is the definition in reverse direction. You are provided with 1 mole of NaCl and you now want to separate them into 1 mole Na plus and 1 mole Cl minus. For that purpose, you have to spend some amount of energy. That energy is called lattice energy. During the combination of 1 mole Na plus and 1 mole Cl minus, around 786 kilojoule per mole energy is released. Okay. 787 kilojoule per energy is released. So we are putting a sign negative because that much of energy is released and is an exothermic process. When the energy decreases to this level, system is that much stable. Now you want to split NaCl into Na plus and Cl minus. Then you have to spend this energy to that system. You have to supply this amount of this quantity of energy to NaCl. Then only that can be separated. You have two ionic compounds AB and CD. AB lattice energy is 700 and CD it is 800. Which is more stable? CD is more stable. Why it is so? During the formation of CD, 800 kilojoule energy is released, but here 700 only. To separate AB, we have to supply 700 kilojoule, but in order to separate CD, we have to give more energy. That means CD is more stable. That concept you have to remember first. Otherwise, lattice energy will be confused. More the energy released, more will be the stability. So, lattice energy of an ionic compound is also useful to predict the stability of ionic compound. Greater the amount of energy released in the form of lattice energy, greater will be the stability of the system. More negative the value, more will be the stability. Negative sign just indicate that energy is released. To find out the lattice energy of an ionic compound, we have Born-Lande equation and Born-Haber cycle. Born-Lande equation and Born-Haber cycle. At first, you have to see Born-Lande equation. It is a theoretical treatment for calculating the lattice energy by an equation directly. Derivation of this equation is not necessary for complementary students. U0, that is lattice energy, equal to minus N0 into A Z plus Z minus E square by 4 pi epsilon 0 R0 into 1 minus 1 by N. Here U0 is lattice energy, N0 is Avogadro number, Z plus charge of the cation, Z minus charge of the anion, E the charge 1.6 into 10 raised to minus 19 coulomb, square of that, epsilon 0 permittivity of this free space, R0 is the distance between the cation and anion in ionic compound. N is called Born exponent. Here A and N. A is called Madelung constant and N is called Born exponent. They are characteristics of the geometry of ionic crystal. It may be FCC, CCP or HCP. By changing or by varying the arrangement, this value can also be changed. These are dimensionless constants, characteristics of the crystal. A is the Madelung constant, N is the Born exponent. In problem, they will give the value of A and N. E0 permittivity of free space is 8.854 into 10 raised to minus 12 Coulomb square, meter inverse, joule inverse. Substituting the value of R0 and charge. For NaCl charge is plus 1 and minus 1. Zinc chloride charge is plus 2 and minus 2. Like that. By substituting these values, you can calculate lattice energy. Another way of calculating lattice energy is Born-Haber cycle. It is a thermochemical method and also a theoretical method based on Hess's law of constant heat summation. What is Hess's law? Total energy change in a chemical reaction is same, whether it takes place in a single step or many steps. That you have studied in thermodynamics of +1. In order to form NaCl, we have sodium as the metal and chlorine as the non-metal. Sodium normally is a solid at room temperature. So that sodium solid first changes to sodium gas. In order to convert a solid to gas directly, we have to supply an amount of energy called sublimation energy. So we have written it as delta H sublimation. When sodium changes to gas, we can make it sodium ion by removing its outermost electron. For that purpose, we have to supply ionization energy to remove that electron in the valence shell. So that energy is called delta H ionization. So by two steps, we convert sodium to sodium ion. First sublimation and second ionization. Parallelly, in the case of chlorine, we are considering half Cl2. Cl2 is bonded. We need chlorine atom. So bond is to be cleaved or dissociated. So we have to spend bond dissociation energy. When one chlorine is broken, two chlorine atoms are formed. But we need only one chlorine atom. So half of the bond dissociation energy is needed. When bond dissociation energy is completely utilized, two chlorine atoms are formed. So we don't want two chlorine atoms, we need only one chlorine atom, so we have to spend half. That chlorine atom now changes to Cl minus ion by accepting one electron. That change is called delta H. Delta H electron gain, Eg, electron gain enthalpy or electron affinity. Now we have Na plus and Cl minus. When 1 mole of one mole of Na plus combine with 1 mole of Cl minus, definitely you will get NaCl. During this process, some amount of energy is released. That is called lattice energy, U0 of NaCl. At the same time, when we have another possibility to get sodium chloride, you have to place solid sodium and you can pass chlorine gas over it and heat it continuously. Then they will combine to form NaCl. Sodium directly combine with chlorine to form sodium chloride. During that reaction, some amount of energy is released, that is called delta F, enthalpy of formation. It is the energy change takes place when 1 mole of the compound is formed directly from its constituent atoms. Sodium and chlorine directly combine to form NaCl. That change is called delta HF. So the same product or same reaction happen in a single step here, but it is in many steps. In both cases, product is same and reaction is same. According to Hess's law, total energy change is equal whether it takes place in a single step like this or many steps like this. So delta HF of NaCl, delta HF means enthalpy of formation of NaCl equal to sum of all these steps. Delta H sublimation of metal, delta H ionization of metal plus half into bond dissociation energy of non-metal plus delta H electron gain enthalpy of non-metal plus lattice energy. What actually we have to calculate here is lattice energy. Therefore, lattice energy U0 NaCl equal to delta HF, that is there in the left side, and all other parameters can be taken to that side. So delta HF minus delta H sublimation plus delta H ionization plus half into bond dissociation plus half into electron gain. If you remove this bracket, you have to put minus sign here, here and here. So both equation can be used with or without bracket. Next one is other applications of Born-Haber cycle. First one is one application we have already studied, that is the determination of lattice energy. Additionally, we have few more applications that we are discussing here. First one is delta HF formation. That means if you know delta H sublimation, delta H ionization, bond dissociation energy, delta H electron gain and lattice energy, you can calculate delta HF, that means enthalpy formation. Second one, delta H solution can be calculated. If you know lattice energy and delta H hydration, when we add NaCl to water, Na plus ion surrounded by water and Cl minus ion is also surrounded by water. Na plus surrounded by water and Cl minus is also surrounded by water. That is called hydration. During the hydration process, some amount of energy is released. That is called hydration energy or delta H hydration. During the formation of NaCl, some amount of energy is released. That is not in water. During the formation of NaCl, first lattice energy is released. That NaCl is added to water. Then hydration energy is released. If the released hydration energy is greater than lattice energy of the NaCl, then only NaCl is soluble in water. So, to become soluble in water, delta H hydration should be greater than delta H lattice energy. ഹൈഡ്രേഷൻ എനർജി ലാറ്റിസ് എനർജിയേക്കാൾ കൂടുതലാണെങ്കിൽ മാത്രമേ ലാറ്റിസ് എനർജിയെ കവർ ചെയ്ത് ആ കോമ്പൗണ്ട് വെള്ളത്തിൽ ഡിസോൾവ് ചെയ്യാൻ പറ്റൂ. ഈ രണ്ട് സംഭവം കൂടി ആഡ് ചെയ്യുന്ന സമയത്ത്, അതായത് ഡെൽറ്റ എച്ച് ഹൈഡ്രേഷനും ഡെൽറ്റ എച്ച് ലാറ്റിസ് എനർജി കൂടി ആഡ് ചെയ്താൽ ബാക്കി വരുന്നത് എന്താണോ അതാണ് ഡെൽറ്റ എച്ച് സൊല്യൂഷൻ ഓർ ഡിസൊല്യൂഷൻ. So delta H solution can be calculated if we know delta H hydration and lattice energy. Another one, stability of ionic compound can be calculated. Higher the lattice energy, higher will be the stability. CFSE calculation is other application. Lattice energy data determined using this Born-Haber cycle is useful in the evaluation of CFSE, crystal field stabilization energy of complex compounds. Solubility prediction, that is another application that we have seen here. Hydration energy should be greater than lattice energy, then only soluble. Determination of electron affinity. If you follow this equation, if you know all the parameters except electron gain enthalpy, then that parameter can be calculated. But for this calculation, you should know the value of delta HF. These are the basic applications of Born-Haber cycle. Thank you.